We'll begin with the basic food chain that we use to explore the movement of matter and the cycling of matter through ecosystems, only this time we'll look at it in terms of energy and the movement of energy into and out of ecosystems. So here's the food chain with producers, the grass at the bottom, herbivores such as say grasshoppers in the middle, and carnivores at the top, such as say birds. And we have energy moving in the form of chemical potential energy from the producers to the herbivores to the carnivores. The question is, where does that energy come from in the first place? The answer to that question is that the original source of energy for ecosystems is in fact the sun. So the supply of sunlight to the grass allows energy to be trapped by photosynthesis into the grass itself and allows the grass to grow. So let's say for this amount of grass in a typical day that the sun delivers 40,000 kilojoules of light energy to the grass to be used for growth. But the thing is, most of that energy actually isn't locked away in the grass, because most of that sunlight energy is in fact reflected by the grass and goes back into the atmosphere as light and heat. And so of the 40,000 kilojoules that's landing on the grass each day, you would expect typically as much as 38,000 kilojoules to be reflected and radiated back into space. And so what that means is that of the 40,000 kilojoules that landed on the grass, only about 2,000 kilojoules is in fact locked away into the growth of the grass in terms of organic chemical potential energy by photosynthesis, which is a chemical process. As I move through here, we'll start to put numbers into this diagram to try and account for the energy. And the point of it is to account for the energy that lands into the food chain. So of the 40,000 kilojoules that has already landed on the grass, we've accounted for 38,000 kilojoules reflected back into space and 2,000 kilojoules that has now entered the food chain. So the question is, what happens to that 2,000 kilojoules? Well, some of it's passed on to the herbivores, and the kilojoules that are passed on to the herbivores are therefore available to be passed on to the carnivores. And typical figures for that would be of the 2,000 kilojoules in growth of the grass in a typical day, there's much as say 320 kilojoules might be passed on to the herbivores, and of that 320 kilojoules which is in the herbivores, perhaps about 40 kilojoules will be eaten and locked away into the carnivores. So well and good, of the 2,000 kilojoules we've accounted for some, but there's a big gap there where we're missing a whole lot of those kilojoules, a whole lot of that grass. And so what's missing? What's missing from this diagram? Where else could that energy go? Well, one place where it could go to is the decomposers. Remember the decomposers? They were picking up things that were the waste, the matter that wasn't eaten in the first place, and the matter that just passes straight on through. And so of the 2,000 kilojoules in grass, some of that grass, remember, has just dropped onto the ground and been decomposed. How much of that has the decomposers got of the 2,000 kilojoules? Of the herbivores, some of it has passed on through, or herbivores have died and landed on the ground. And so how much of that has passed on through, and then the same for the carnivore. So typical figures there would be of the 2,000 kilojoules, as much as say 480 could be passed on to the decomposers. Of the herbivores, 320 kilojoules, as much as 60 could be passed on to the decomposers. And of the carnivores, 40 kilojoules, as much as 8 kilojoules, could be passed on to the decomposers. So we're accounting for some, but we still haven't accounted for all. Let's have a look at the grass. We had 2,000 kilojoules to account for. We've got 480 kilojoules accounted for there, and we've got 320 kilojoules accounted for there, and 480 and 320, that's 800 kilojoules. Where's the rest? Where's the rest of it? Of the 2,000, we're missing 1,200 kilojoules. It must have gone from somewhere. Well, the thing is that every one of these organisms which is in my ecosystem is in fact losing energy as heat all of the time. Even plants produce heat because the chemical reactions that go on in living things are inefficient. Any chemical reaction that goes on in living things is typically around about 90% inefficient. That is, around about 90% of the available energy is lost as heat. So for example, if I burn some of the food I've eaten, the chemical potential energy to move, then of that energy that I've burned, around 10% is used for the movement, and the other 90% actually produces heat, and I tend to get warmer because I move. And the more you move, of course, the hotter you get. you know that from exercise, and so that's evidence that in fact your chemical reactions in your body are inefficient and energy is being lost as heat all the time. So from every step of the way, what is happening from every organism in this is energy is being lost to the atmosphere as heat, and we would expect heat energy to contribute 2,000 kilojoules each day, because 38,000 was reflected back here, 2,000 has entered the system, we expect to see 2,000 exiting the system. So when I clean this up a little bit and formalize it, I've got heat arrows heading out from every step of the system: the producers, the herbivores, the carnivores, and the decomposers, going back into the atmosphere, which is going to be returned to outer space and lost. To put figures on it, sure enough, I find that the decomposers are contributing 548 kilojoules, the carnivores contributing 32 kilojoules, the herbivores contributing 220 kilojoules, and the producers contributing 1,200 kilojoules. If I add that up, it comes to 2,000 kilojoules.